Both of these are previous AIPMT questions from Ray Optics. Let's analyze this question. Let's analyze this, starting with this question first. For a given incident ray, this is the incident ray shown in the figure. The condition for the total internal reflection is, that means for this particular angle of incidence, light ray has to reflect back into the same medium. That's the total internal reflection, right? So, first of all, for this angle of incidence theta, which can be called like an angle of incidence for a critical angle, for total internal reflection at this x, at x, we know the condition that refractive index mu equal to 1 by sin c. What is this c? See, this is theta, that is 1 by sin theta. But we don't know the value of the theta. But we know this angle as r. If I extend, this is the right angle. So if this is r, this is 90, this theta becomes 90 minus r. 1 by sin 90 minus r. Is it not? It's right angle triangle. The total angle in a triangle is 180 degree. We know 1 sin 90 minus r equal to cos r. So the equation is, for total internal reflection, mu has to become 1 by cos r, where r is the angle here. Here is the r. But look at this. At this surface, there is an angle of incidence of 45, angle of refraction as r, and I can apply the Snell's law. Let me call that angle as, that location as y. Applying Snell's law at y gives you what? Mu equal to sin I by sin r. We know that, right? I at this surface is 45 by sin r. I don't know the r. So from here we can say mu equal to sin 45 is 1 by root 2 and then sin r. You got one value of mu here. You got the same value of mu here. This is at x. This is at y. This is at x. But both are the refractive index of the same pair of the media. So I can equate both these refractive indexes. This is 1. This is 2. I will say, as 1 is 2, refractive indexes are same. I can write 1 by root 2 sin r equal to 1 by cos r. That implies sin r by cos r, by taking the sin r to the other side, is 1 by root 2. That implies sin by cos is tan. Tan r is 1 by root 2. What the problem is? The condition for the total reflection will be satisfied if the refractive index of the block is. What is that mu you want to calculate, right? But we know what do you mean by this tan r equal to 1 by root 2? If you draw a right angle triangle, if this angle is r, tan means opposite side by adjacent side, 1 by root 2. So this hypothesis becomes square root of root 2 square plus 1. That becomes then automatically root 2 square is 2 plus 1 is 3, root 3. Now if I have to write refractive index, this is the refractive index formula. Mu equal to this one, 1 by root 2 sin r. What is this sin r? See here, this is r. Sin r means opposite side by hypothesis. that's 1 by root 3. So if you reverse the fraction, it becomes square root of 3 by 2. So the answer for this problem is square root of 3 by 2. This is how we have to solve the problem. You can relook and see. So what I have done in principle is applied Snell's law at junction x and y, found refractive index in both the cases, just equated both of them and simplified them. That is that simple, right? So whenever you see a problem, you shall try with a cool head so that you will be able to solve it, right? That is this first question. Let me solve. There is another question that is also depending on a critical angle, right? Let's have a look at this question. This is AIPMT 1994, quite old. A point source of light placed 4 meters below the surface of the water of refractive index 5.3. So what happens is, there is water a point source is placed at a depth h. This is the point source. Refractive index is given. The minimum diameter of the disc which should be placed over the surface on the water to cut all the light coming from the water. Let us see what happens actually. So light from this point source strikes this surface like this. Here there is a particular angle called angle of incidence. If any of this angle of incidence is less than critical angle, light ray will go to the other side, that is through this air, so that you will be able to see it, right? So once if it is critical angle, light ray will graze the boundary. So light ray, or else further, if the angle of incidence is more than critical angle, it reflects back. So what his question is, what shall be the diameter of the disc that should be placed on the source on the surface of the water to cut off all the light coming from the water. So one thing that you can understand very carefully is, light comes to the other part, that is to the screen, that is to the air, provided angle of incidence is less than critical angle. That means on the other side also, if you draw the diagram, until the angle of incidence is critical angle, light ray will go to the other side, that is onto the air. Beyond that, anyway light either grazes or reflects back, then you need not put any disc on that. So up to where you have to put a disc? You have to put a disc until the angle of incidence in the bottom is less than the critical angle. That means this is the disc that you are keeping. This is the disc. Now he is asking what should be the diameter of the disc. Then he is asking what should be the diameter of this disc is. So you need to know radius, so you can find the diameter, right? So if this is critical angle, this also becomes automatically a critical angle, and we can write at critical angle mu equal to 1 by sin c. See, this is c, this is h, this is r. This hypothesis becomes root of r square plus h square. 1 by sin c means opposite side by hypothesis, r by square root of r square plus h square. So if you simplify, mu will become square root of r square plus h square by r. Now you want to calculate that radius, right? So you cross multiply now. What happens when you cross multiply? You can write the value of the, you can just cross multiply or square that. Mu square equal to r square plus h square, this root will go by r, then cross multiply mu square na, so it becomes a square, mu square r square equal to r square plus h square. So mu square r square minus r square equal to h square, r square of mu square minus 1 equal to h square. r equal to h by square root of mu square minus 1. That's the radius of the disk that we need to keep. How much is that? H is given for you as 4. Mu is given for you as 5 by 3. You have to square it. 25 by 9 minus 1. That is 4 by 9 is the LCM. 25 minus 9. 4 by 16 by 9, that is 4 into 3 by 4. So the radius of that is 3 meter. Be careful, that's the radius, but what you want is what shall be the diameter. Diameter is double to that. That implies diameter is 6 meters. So you shall keep a disk of diameter 6 meters on the surface of the water, so that light within that range will try to go this way, but that is being stopped by this disk. Anyway, beyond that critical angle and above critical angle, light ray comes back, so you need not stop it. That's how we have to solve the problem. Thank you.